Hello and welcome to helpyourmath.com. In this video, we're going to look at some very common parent functions, including linear functions, absolute value functions, quadratic functions, cubic functions, square root functions, and reciprocal functions. So, what about parent functions? It's good to know basic information in the shape of common functions. Once you are familiar with the shape of the parent function, you can use that information to graph transformed functions of those same type. What we're going to discuss for each parent function is the domain and range, where it increases, decreases, or is constant, and any intercepts that the graph may have. Let's get started. So first we have the linear function, and the parent function for the linear function, this is called the identity y equals x. What does the graph of y equals x look like? Well, keep in mind that on the graph it would be at -4, right? Because whatever x is, y is 2. -3, -3, -2, -2, blah, blah, blah. And so when we use a straight edge to graph those, we get a straight line with a nice 45-degree angle. All right, so what's the domain of this? Well, is there any value for x that we're not allowed to plug in? No, it's linear. We're allowed to plug in anything. So the domain is -infinity to infinity. How about the range? Are there any y values? Well, if we're hitting every x value, we must be hitting every y value too. So the range is going to be from -infinity to infinity also. So then I ask, what is it doing? This is where is it increasing, decreasing, or is it constant? For this linear function, it's going to be increasing everywhere, right? So we're going to say increasing, and we're going to put the interval on which it's increasing. It's increasing from, well, everywhere, so it's -infinity to infinity. And lastly, what are the intercepts or intercept? So intercepts, those are where the graph crosses the x or y axis. It looks like it crosses at the same time right here, and we would have one intercept at 0, 0. So this would be both the x-intercept and the y-intercept, since it's at the origin. So this is the parent function for linear equations. And we are probably already familiar with linear equations. We don't need too much information about this, but this is the parent function. So there it is. Okay, the next one we're going to talk about are absolute value functions. So the parent function for the absolute value is y equals the absolute value of x. What does that look like? Well, as long as x is positive or 0, then y will be the same, right? Because the absolute value just indicates that it's non-negative. So we would have a point here at 0, 0, 1, 1, 2, 2. What about when x is negative? Well, any negative value for x, we take the absolute value, it's going to turn that value positive. So if x is -1, y will be +1. If x is -2, y will be +2, and so on. We use a straight edge to graph this, and we end up getting a kind of like a V shape, which I always like. We can always remember the absolute value, the value, because it looks like a V. Haha, great, isn't it? All right, what's the domain on this bad boy? Are there any restrictions on x? Is there anything I'm not allowed to plug in? No, everything's fair game here, so the domain is going to be from -infinity to infinity. How about the range? Are there any values for y that we can't attain? Yes, there are. Y can't be negative, right? Because if we're taking the absolute value, it's going to turn it non-negative. So the range, the minimum point is at 0 and it's included. So we include 0, and then it goes up to +infinity. So we close it with a parenthesis. What is this graph doing? Well, until we get to 0, although my arrow is going the wrong way, until we get to 0, it's going down, 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 down. So we say that this graph is decreasing from -infinity to 0, and then it's increasing from 0 to infinity. Notice that when I do my intervals for increasing and decreasing, we never include endpoints. So 0, we don't include 0. It's not doing anything at 0, because that's actually where it's switching direction. So it's decreasing until 0, we don't include it. It starts increasing at 0, we don't include 0. Okay, and then what are the intercepts or intercept? Well, in this case, there's only one place where it hits either axis, and that's the origin. So we would say that the x-intercept is equal to the y-intercept, which is equal to 0, 0. So that would be the intercept for this graph. And again, what we want to really focus on in this video is the shape of each type of parent function, because then when we get to transformations, we basically have to remember this shape and just kind of move it around the graph. All right, next we have our quadratic function. What does the quadratic function look like? That's the parent function is y equals x squared. Y equals x squared. It might be helpful to make a table. Sometimes I like knowing the table of values for these, because that will help me with my transformations. So if we make a table of values, we have x and y, or f of x, and we'll use 5 values. We'll use the standard -2, -1, 0, 1, and 2. So when x is -2, we square it. -2 quantity squared is +4. When x is -1, -1 quantity squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So this graph, -2, 4, is up here. I don't have a nice picture for this one, so I'm going to have to do the best I can. -1, 1, 0, 0, 1, 1, 2, 4. The shape of this graph is called a parabola, and it's a nice smooth curve. So unlike the absolute value function, it's not a point at the bottom of it, it's a nice smooth curve. And this thing here is called a parabola. That's the shape of a quadratic, is called a parabola. All right, what other information about this parabola? The domain, or this quadratic I should say. The domain, any restrictions? No. Polynomials will never have restrictions on their domain. So it's going to be from -infinity to infinity. How about the range? Well, because we're squaring things, it's same idea as taking the absolute value in that we're never going to have a negative. So the range here is going to start at 0, where 0 is included, and it goes up to infinity. So that would be our range, 0 to infinity. What is this graph doing? Well, it's doing two things, right? It kind of stops right here, it switches. So on the left of that line I just drew, it's going down. So we're going to say it's decreasing from -infinity to 0. And again, we don't include endpoints in the increments, in the intervals, excuse me. And it's increasing. It starts increasing at 0, and it will continue forever and ever and ever. It's going to keep going up, 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 as long as x is positive. And lastly, the intercept. Again, we have one intercept. It's the same x-intercept as the y-intercept, which is the origin, which we say 0, 0. Okay, the next parent function is our cubic function. The cubic function is given by the equation y equals x cubed. I like to make my table of values to see what's going on. So we're going to have x and y, and I can use my standard -2, -1, 0, 1, and 2. If I plug in -2 for x, -2 quantity cubed is -8. -1 quantity cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So looking at this, -2, -8 would be down here. -1, -1 is here. 0, 0 is here. 1, 1 up here. And 2, 8 is off my screen. It's going to be right up there. This again, because it's a polynomial, will be a nice smooth curve, just like our quadratic. Whoop, can't get to 2 too quickly. Go up there. And so our graph will look something like this. And of course it will be a little bit neater if I could get a nice picture, but I didn't, so we're stuck with that. I don't like that. We're going to get rid of that. Oh, apparently I'm starting the whole thing over. Let's try this again. Nope, that's equally as terrible. Third time's a charm, right? Here we go. Okay, beautiful. That's exactly what I wanted it to do. Okay, let's talk more about our cubic function. So the domain of our cubic function, it's a polynomial. It has no restrictions on the domain, -infinity to infinity. The range, well, in this cubic function, we can go as low as we want and we can go as high as we want. So the range would be from -infinity to infinity. What is this graph doing? Well, the entire graph, it's always going up. Every point that's to the right of some other point will have a larger output than the point that's to its left, right? So anywhere on this graph, it's increasing. So we're going to say it's increasing the entire graph from -infinity to infinity. And last, what are the intercepts of this? Well, just like all our other ones, we have an intercept at 0, 0. So our x-intercept is the same as our y-intercept at 0, 0. And that's our cubic function. Next up, we have the square root function. The square root function is given by y equals the square root of x. Now, when I go to make my table of values, you can even see on my graph, it's a little bit different than the past because I can't plug in -2. -2, the square root of that is an imaginary number. It's not in the real number system. We can't graph an imaginary number on a real number plane, so therefore we can't use -2. We also can't use -1. In fact, the smallest value we can use is 0. And then when I go to plug in the rest, I don't want to do, let's say, 0, 1, 2, 3, 4, because I have to take the square root of these numbers. So I probably want to choose numbers that are going to have nice square roots. Therefore, I'm going to look at the perfect squares, specifically the perfect integer squares. So the first perfect square after 0 is 1, after 1 is 4, and after 4 is 9. Now I can take the square root of these really nicely. The square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. When I go to graph these, we have 0, 0, 1, 1, 4, 2, and 9, 3. This is just a nice curve. So it'll look kind of like that. And it is curved. I know it doesn't look super curved, but I promise it is. More information about this, the domain. It's not all reals this time, right? It starts at 0. So the domain, we include 0, and then it can be any positive value beyond after 0. The range, same deal. It's going to start at 0, and it can be any positive number after 0. What is this graph doing? Well, starting from 0, it is continually increasing. So because it's always increasing, we're going to say that it's increasing on the interval, which is the entire domain, but we don't include 0, so it's going to be from 0 to infinity. And guess what the x and y-intercept is? That's right, it's 0. The x-intercept is the same as the y-intercept, which is the origin 0, 0. So this is our square root function. One left. The last parent function we're going to look at is the reciprocal function. The reciprocal function is given by y equals 1 over x. And can we use our famous -2, -1? Yes, we can. We can use -2, we can use -1. This we want to get a little bit, we're going to get a little sneaky, and I'm actually going to use -0.5, and you'll see why. Unfortunately, I can't use 0, because if I plug in 0, I would have 1 over 0, which does not exist. It's not a real number. So we're going to skip over 0. Now I'll do some positives, 1/2, 1, and 2. If we plug in -2, that would be 1 over -2, which would be -0.5. -1, 1 over -1 is -1. 1 over -0.5, so this is the reciprocal. What's the reciprocal of -1/2? That's right, it's -2. The reciprocal of 1/2 is 2. The reciprocal of 1 is 1. The reciprocal of 2 is 1/2. Or you can plug these in for x. Either way, these are the values we're going to end up with. So what does this graph look like? -2, -0.5, -1, -1, -0.5, 2 will be like right there. We connect all the negatives with a nice smooth curve. And then the positives, we have 1/2 and 2, 1, 1, 2, 1/2. We're going to do the same thing. And so this is what this reciprocal function will look like. Kind of different than the other ones, isn't it? Well, what's the domain here? We can plug in every value in the entire real number system has a reciprocal except for 0. So the domain here is going to be from -infinity to 0, and then from 0 to infinity. The range is going to have the same issue. We're never going to get 0. It's just never going to happen. It's never going to cross that y-axis. So the range is going to be from -infinity to 0, and then from 0 to infinity. What is this graph doing? Oh boy. Well, it is on the left-hand side, it's actually decreasing the entire time. So while here it kind of looks like it's going to be flattening out, it will never flatten out. It is getting closer and closer and closer to that x-axis, but it's never going to reach the x-axis. So we're going to say that it's decreasing from -infinity to 0. And then over here, it is also decreasing. Whoa, this is just a big fat decreasing graph. So it's also decreasing from 0 to infinity. It's forever decreasing no matter what happens. Unless you plug in 0, in which case the graph will explode or something. I don't know about that, but we can't plug in 0. And the intercepts, uh-oh, this one broke the mold again. There are no intercepts on this graph. So intercepts, there are none. And that's it for our reciprocal function. That's it for our parent functions. So again, the important thing here is just recognizing the shape. If I held up a graph of something, would you recognize which type of graph it is? That's what we want to focus on here. Thank you for stopping by.